Hi everyone, it's me Prathami and I'm back with the part 2 of the computer codes video. In this video, we are going to explore about BCD and the Gray Code and few of the conversions. If you have not watched the part 1 of the video, I request you to please watch that video first for better understanding of the concept. The link to the part 1 video is provided in the description below. So, in this video, we will discuss about the numeric codes, that is BCD and Gray code. Binary coded decimal, or in short BCD, also sometimes called as 8421 code, describes the encoding of decimal numbers where each decimal digit is represented by a fixed number of bits, usually 4 or 8. I said 8 bits because sometimes special bit patterns are used for a sign or other indicator such as error or overflow. This is how you can write BCD code by using 4-bit patterns, usually called as nibble. It ranges from 0 to 9. With 4 bits, you can also represent 10 to 16, but in BCD they are not valid and are called as don't cares or pseudo-tetrads. There are two variations in this: unpacked BCD and packed BCD. Unpacked BCD usually implies a full byte that encodes a single digit within a single byte, including a sign. Packed BCD usually implies half a byte that encodes two digits within a single byte by taking an advantage of the fact that 4 bits are enough to represent the range from 0 to 9. Packed BCD is more efficient in terms of storage usage than unpacked BCD. Shifting and masking are used to pack or unpack BCD digit. Now you know that BCD takes on 4 bits. So, with these 4 bits, we can represent 16 different combinations of bits arranged from 0000 to 1111. But out of this, only 0000 to 1001, that is 0 to 9 in decimal, are enough to represent decimal digits. A decimal number 10 can be formed with two nibbles. A nibble is a group of 4 bits, that is 0001 to represent decimal number 1 and 0000 to represent decimal number 0. That's why we don't need 1010 to 1111 bit combinations. These bit combinations in BCD are called as don't cares or DC or pseudo tetrads. Hence, we can properly define don't care condition as the set of inputs which is not a valid combination of bits in digital circuit. These conditions can be used for further simplification of Boolean expressions so that the circuit can be implemented with minimum number of gates, and that's where the K-map comes in. BCD arithmetic is difficult and requires more complicated circuits and need more number of bits than binary. BCD is commonly used in digital systems that require precise decimal arithmetic, such as calculators, cash registers, and accounting systems. It is also used in real-time clock circuits and measurement systems. Today, BCD data is still heavily used in IBM databases such as IBM DB2 and processors such as Z architecture and Power 6 and later Power ISA processors. In these products, the BCD is usually zoned BCD, as in ASCII or ASCII, packed BCD, 2 decimal digits per byte, or pure BCD or unpacked BCD encoding, that is 1 decimal digit stored as BCD in lower 4 bits of each byte. All of these are used within hardware registers and processing units and in softwares. We shall now see gray code. Gray code is also known as the reflected binary code (RBC) or reflected binary (RB). This method is devised by Frank Gray in 1953 and hence the name. Frank Gray was a physicist and a researcher at Bell Labs who made various innovations in television, both mechanical and electronics. Gray code is such an ordering system that two successive values differ in only one bit. This is the reason why gray code is also sometimes known as the single distance code or unit distance code. This is how one can generate the gray code by mirroring and prefixing steps. Commence with the simplest gray code possible for a single bit. Create a mirror image of the existing gray code below the original values. Prefix the original values with 0 and the mirrored values with 1s. Repeat steps 2 and 3 until the desired width is achieved. Advantages: gray codes are mainly used to prevent spurious output from electromechanical switches and to facilitate error correction. It simplifies logic operation and reduces errors in practice. Disadvantages: increased complexity, increases computational overhead in digital systems, not suited for arithmetic operations like addition and subtraction. Limited scalability. Gray code works well for small number of bits, but as the number of bits increase, complexity increases and becomes inefficient. Now let us look at the applications of gray code. Gray code is used to encode the position of a motor. Let me elaborate on this. The disk is divided into 8 sectors and 3 concentric circles. Each section holds 1 bit value. So, each sector holds 3 bit values. Let us see what happens when the shaft motor moves from one sector to another. In binary system, during transition, when it reads from 001 to 010, the MSB will have no change. It will be 0 as it is, but the rest of the 2 bits will hold either 0 or 1. So the encoder will encode it as 000 or 001 or 010 or 011. The reading can go wrong if it reads 000 or 011. The whole purpose of designing will fail. Even worst when the transition is from 111 to 000 or from 011 to 100. But with gray code, since there is only one bit change, the reading cannot go wrong. Apart from this, gray codes are used in error correction, telegraphic codes, Boolean and circuit minimization, genetic algorithms, angle measuring devices, and so on. Now let us look at the conversions. Since we see different applications of different codes at different times, we surely need convergence. So let us now see in brief the convergence to and from the following: BCD to ASCII, BCD to ASCII, decimal to BCD, binary to BCD, binary to gray code, and BCD to gray code. BCD to ASCII. In order to get ASCII code, just prefix with 0011 to 4-bit BCD code. Example, 0100 is BCD 4. Just prefix it with 0011 to get 00110100, which is ASCII 4. Similarly, remove 0011 to get back to BCD 4. BCD to ASCII. In order to get ASCII code, just prefix with 1111 to 4-bit BCD code. Example, 0100 is BCD 4. Just prefix it with 1111 to get 11110100, which is ASCII 4. Similarly, remove 1111 to get back to BCD 4. Decimal to BCD. A decimal number can be converted to BCD by writing the 4-bit binary equivalents of all the digits in the decimal in the same order. For example, 642 has 3 digits. If we write these digits as 4-bit binary numbers, we obtain the following: 6 in base 10 is equal to 0110 in base 2, decimal 4 is equal to 0100 in binary, decimal 2 is equal to 0010 in binary. Writing those binary numbers with the same order as decimal gives us BCD equivalent, that is 642 in decimal is equal to 0110 in BCD. In order to get back to decimal, just arrange the bits into a group of 4 bits starting from the rightmost bit and convert each group into decimal. Then writing the same numbers in the same order, we get the decimal number. Let us take the same example. 0110 is 642, that is decimal 642. Binary to BCD code. In order to convert from binary to BCD, we should first convert the binary number into decimal number and then from decimal to BCD. To convert binary to decimal, I have done the video, just watch it, whose link is in the description below. And we just discussed on how to convert from decimal to BCD. So let us directly see an example. Consider a binary number 101010. One thing to keep in mind, just looking at these ones and zeros, do not confuse yourself and group them wrongly into 0010 and 1010. This is completely wrong. We have to first convert them into decimal by writing 2's powers like this: 1, 2, 4, 8, 16, 32. Now add those numbers wherever you find 1, that is 32, 8 and 2. Adding up equals to 42. Now convert 4 and 2 into 4-bit binary number like this. That gives the BCD equivalent 01000010. Now to get back to binary again from BCD, we follow the same procedure with a little modification. That is, we convert BCD number to decimal equivalent and then from decimal to binary. Example, consider BCD number 01000010. Starting from the leftmost bit, make them into group of 4 bits, that is 0100 and 0010. Write the decimal equivalent of each nibble. 0100 is 4 and 0010 is 2, that is 42. Now use the long division method to convert from decimal to binary. So after calculation, the binary equivalent we get is 101010. For computer implementation, we have an algorithm known as double dabble algorithm. This is how the implementation is done. And this is the reverse algorithm. Binary to gray code. Here we rewrite the most significant bit, that is MSB, then compare the adjacent bits. If they are same, write a 0, and if they are different, write 1. Example, 1101010 in binary. Write the MSB, that is 1, as it is. Now compare MSB and the digit next to it, that is 1 and 1. They are same, so we write a 0. Now next two digits are compared, that is 1 and 0, and since they are different, we write a 1. Next two digits are 0 and 1. They are different, so we write a 1. Next is 1 and 0. They are different, so write 1. Next is 0 and 1. Different, so write 1. And 1 0, different again, write 1. So the gray code equivalent of 1101010 is 1011111. Now let us see how we can go backwards, that is from gray code to binary. Here also we write the MSB as it is. Then compare second bit of the gray code and the first bit of the binary code. Continue comparing till there are no bits to compare. Example, consider the gray code 1011111. Write the MSB as it is, that is, write 1 as it is. Next we compare second bit of the gray code, that is 0, and first bit of the binary, that is 1. Since they are different, we write a 1. Now compare the third bit of the gray code, that is 1, and the second bit of the binary code, that is 1. Since they are same, write 0. Similarly, compare others and we get 1101010. BCD to gray code. While converting from BCD to gray code, first convert BCD to binary and then convert from binary to gray code. We have already discussed to and from binary some time ago, so let me explain it with an example. We have BCD code 01000010. First convert it into decimal by grouping them into 4 bits group and then write the decimal equivalent of each 4-bit group, that is 42. Now convert it into binary, that is 101010, and then apply binary to gray code conversion, that is write the MSB and compare the adjacent bits. By doing this, we get the gray code equivalent as 111111. And to convert from gray code to BCD, first convert gray code to binary and then convert from binary to BCD. Example, here is the gray code 111111. First, we have to convert it into binary, that is 101010. Then write the decimal equivalent of it, that is 32 plus 8 plus 2, which is equal to 42. So the decimal to BCD conversion will give you 01000010. The confusion between binary and BCD. Let us understand by comparison. BCD is nothing but our decimal number system. In decimal number system, we write 0 to 9 using the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whereas in BCD, we write the same thing using the symbols 0000, 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1000, 1001. In binary, we use symbols 0 and 1. Just imagine 0000 as one symbol denoting 0 in BCD. Similarly, 0001 is another symbol denoting 1 in BCD, and so on. For example, decimal number 642 can be written in BCD as 0110, 0100, 0010, and in binary as 101, 000010. Let us look at the incrementing numbers in decimal, binary, and BCD. BCD uses two nibbles to represent decimal 10, 11, 12, 13, 14, 15 after the ninth digit. Since BCD is coded in binary, it is likely for a BCD counter to naturally increment to binary 1010, that is decimal 10, after 1001, that is decimal 9. We should make sure that does not happen because 1010 is not a BCD digit. That is, as I mentioned earlier, 1010 to 1111 nibbles are not valid in BCD and are called as don't cares. The main confusion between binary number system and BCD number system is the similarity. That is, when we write 0 to 9 binary number in a group of 4 bits, they look exactly similar. So, during conversions from BCD to gray code and others, when we have to translate BCD to binary, we have to be careful because it will give correct result till 9, but beyond 9, if you do not translate into binary, you might end up getting wrong result. I hope you have understood something over here. If you have any doubts, then please ask me in the comment section below. I will be happy to respond. If you have understood, then make sure to hit the like button and subscribe to my channel because I have more such videos coming your way, and please share with those who might find the stuff useful. Thanks so much for watching this video. See you soon in next one.